On August 27, 2025, astronomers used the powerful 8.2-meter Gemini South telescope in Chile to take detailed images of the interstellar object known as 3I-ATLS. With the help of the Gemini Multi-Object Spectrograph, GMOS, they discovered a faint, teardrop-shaped tail pointing away from the Sun. At that time, 3I-ATLS was located about 2.59 times farther from Earth than the distance between Earth and the Sun. The Gemini South Observatory, where these observations were made, is situated high in the Andes Mountains on a peak called Cerro Pachón. The images were captured through 4 different filters, each focusing on a specific wavelength of light, ranging from ultraviolet to near-infrared. These filters, labeled U, G, R, and I, revealed a clear tail stretching approximately 30 arcseconds across the sky, which is equal to about 56,400 kilometers in length. This tail was seen extending toward the southeast, directly away from the Sun. Surrounding the object is a glowing region called a coma, which measured about 10 arcseconds, or 18,800 kilometers wide, much broader than it appeared in earlier images from July 2025. Earlier that month, on August 6th, the James Webb Space Telescope confirmed that 3I-ATLS was releasing a cloud of carbon dioxide gas with much smaller amounts of water vapor and carbon monoxide. These findings matched earlier results from the SPHEREX Space Telescope, which had mapped the carbon dioxide cloud as far as 348,000 kilometers from the object. Based on the data, scientists calculated that the object was losing mass at a rate of about 130 kilograms of carbon dioxide per second, 14 kilograms of carbon monoxide per second, and just 6.6 kilograms of water per second. This very low level of water is unusual for a comet, as most comets release much more water than carbon dioxide. The gas cloud around 3I-ATLS is shaped by the pressure of the solar wind and sunlight, forming its teardrop appearance. One researcher even calculated that the edge of the gas cloud corresponds to the point where the pressure from the solar wind balances out the pressure of the gas escaping from the object. Still, it remains uncertain whether the brightness of the coma and tail comes from dust particles or from small pieces of frozen gas, such as carbon dioxide, carbon monoxide, and water, that have broken off the object's surface. Interestingly, NASA's test satellite had already picked up signs of activity around 3I-ATLS as early as May 2025, when it was still 6 times farther from the Sun than Earth is. At such a great distance, sunlight shouldn't be strong enough to heat ice, which raises questions about what kind of material could be responsible for triggering this early activity. Later, in mid-August 2025, SPHEREX detected strong infrared light coming from the object at a wavelength of 1 micrometer. This suggested either a large solid core or a dense compact cloud of particles reflecting sunlight. The estimated diameter was around 46 kilometers, which would make 3I-ATLS about 1 million times more massive than the last interstellar comet we studied, 2I Borisov. This came as a surprise since we would have expected to discover many smaller interstellar objects before spotting one this large. To make things even more puzzling, 3I-ATLS is moving along a path that closely follows the plane in which the planets orbit the Sun, something that is not expected for objects entering the solar system from interstellar space. A previous study also pointed out that the amount of rocky material drifting between stars is too low to explain the appearance of such a large object during the short time telescopes like ATLS have been searching the sky. Adding to the mystery, new data from the Very Large Telescope in Chile revealed the presence of cyanide and nickel in the gas around 3I-ATLS, but strangely there was no sign of iron. This